Okay, so hi everyone. Good morning and good evening. And this is the second public colloquium of Extreme Universe project. And this time we are extremely happy to have Professor Roberto Emparan from Barcelona. And I think he's been recognized one of the world leading experts of general theoretical aspects of general relativity and gravitation and string theory. And he has been publishing many influential papers, including very famous one on the, for example, black ring solution in 5 dimensions. And also, many of us recognize him in person because he often visits Kyoto and other parts of Japan. So actually, all of us are basically friends of Roberto. And today, he's talking about quantum black holes and holograms. So please start, Roberto.
Yes, thank you. Thank you, Akihiro, for the kind presentation, also for the invitation to join this presentation with you, to share it with all of you, because as we say, I've been friends with many of you for many years, and even if it's, well, I cannot be now in person with you, I'm very glad at least to be here with all of you online. So yeah, so this is the title of my talk. It's a fairly broad talk, I think, and it's also a talk that goes back a number of years, the origin of it. The early ideas of what I'm going to be talking about today, they are more than 20 years old. They date back to work by, well, one of your colleagues, Takahiro Tanaka, and work that I did also a little later in collaboration with Alessandro Fabri and Nemanja Kaloper. And the subject saw a revival a few years ago because there were important developments in it. And well, my collaborators in this recent work are listed over here, or at least the papers that I'm going to be talking about today, or at least that they are going to be mentioned at least today, are these papers which appear, as I said, in recent years, and they are Antonia Frasino, Raimon Luna, Juan Pedraza, one of your colleagues, Ryota Suzuki, Andis Vesco, my former student, Maria Tomasevich, Manus Visser, and Benson Wei. Okay. Now, I think it's very nice to be talking about this subject this year because, well, it's half a century. It's the 50th anniversary of the discovery of black hole radiation by Hawking, which is that discovery launched the era of quantum black holes. So before this year, people had been developing the classical, what people call the classical, or the golden age of classical black holes. In 1974, started the quantum era of black holes. Now, we're talking about black holes, we're talking about quantum. I think that everybody agrees, or mostly everybody agrees, that gravity, classical gravity, Einstein gravity, should be the classical limit of a quantum theory. And if gravity is the limit of a quantum theory, then its objects should also be limits of quantum objects. And in particular, black holes should be classical limits of quantum objects in this quantum theory of gravity. And then, well, we may ask ourselves, what is a quantum black hole then? Do we know what a quantum black hole is? Did Hawking know what a quantum black hole is when he applied quantum theory to black holes? Well, he didn't have a quantum theory of gravity. So instead, what he did is something else. He took an approximation where he studied, instead of a fully quantum black hole, he studied quantum fields in the presence of the black hole, taking the black hole as a fixed classical geometry. And then we usually say that then, well, we say that Hawking discovered that the black hole emits radiation when you consider that quantum fields are in its presence. I think more than the black hole emits radiation, since the black hole is playing here more a passive role, we should say that radiation comes out of the black hole. Because as I say, the black hole is passive, the black hole remains unaffected and remains a classical object in Hawking's calculation. Okay. Now, this idea that the black hole remains unaffected and remains a classical object, well, that's an approximation. And approximations, well, they have their limits of validity. This approximation of considering that the black hole is not affected by the emission of radiation is good enough if the effects of the radiation are small on the black hole. If a very large black hole emits one quantum, then that's going to affect very little. That's what we expect, that it's going to affect very little the properties of the black hole. But this approximation will fail if these effects become large. And the effects can become large for two reasons, because maybe you've emitted a large number of photons, of quanta. So the cumulative effect of all of this emission may have an effect, a sizable effect on the black hole. Or it may be that, say that during stages where the black hole, the emission of a single quantum is a significant process. It changes the properties of the black hole by a large amount. Now, when you cannot apply this approximation that the black hole remains unaffected, then, well, you have to take into account what we call the back reaction of the radiation. So, well, we say that Hawking, I just said, Hawking did not have a quantum theory of gravity 50 years ago. But nowadays, we do have quantum theories of gravity. We do have a good quantum theories of gravity with a complete formulation, where we know that these quantum theories of gravity, these are the holographic theories of gravity that arise from the ADS-CFT correspondence. These quantum theories of gravity, they do have black holes, and so black holes appear in the semi-classical, in the latent limit of these CFTs that give us a complete formulation of gravity, quantum gravity in ADS. So if we have those quantum theories of gravity, then do we know what a quantum black hole is? Well, we don't have a complete answer. Might say, well, if you're so smart that now you have a quantum theory of gravity, can you tell me what a quantum black hole is? Well, what ADS-CFT is kind of saying us in a way that we don't fully understand is that a black hole is some object in this conformal field theory. Typically, these are gauge theories, so objects in the gauge theory are matrices. So a black hole is kind of a latent matrix whose entries, the entries of the matrix, are fastly scrambling. Now, this is kind of a picture. Making it precise and working with it is difficult. So developing better this picture, that's something that many people are working on. That's an important problem, but the picture is still too poorly understood to, for instance, to properly account for the back reaction problem in this full quantum theory of gravity. So instead of doing this, we can try to do something else. We can simplify, not all the way down to the simplification that Hawking did, but we can set ourselves a simpler goal, which is to study the classical geometry of the black hole modified possibly a lot by the quantum effects of the radiation. So this is what we call a quantum back-reacted black hole. The geometry still remains classical, but it has large effects from the quantum back reaction of the radiation. Okay? So this is what I'm going to mean by a quantum black hole. It's not a fully quantum black hole, but at least it incorporates quantum effects in a significant way. And by doing this, one can gain a lot of insight into the problems of quantum physics in the presence of black holes. So what is this problem of the quantum back reaction? Well, the idea is that we're solving here the Einstein equations. Recognize the Einstein equations. This is the Einstein tensor. But we consider that this system, this side of the equation, is classical. This is the classical Einstein tensor and the metric. And in the right-hand side, what we have is the stress tensor, but the fully quantum stress tensor, the normalized stress tensor of matter. Okay? And if you want this to be consistent in the sense that you're not quantizing gravity here, well, you can consider that you have here a large number of fields, so that, well, considering the quantum fluctuations of the metric, it would add just one more quantum field. So if you have a large number of fields, that's going to be a small effect. That's kind of a large n approximation when you have here a large number n of fields. So the limit of large n fluctuations of the metric can be suppressed. So this is kind of the problem that we want to address, to study. This is the problem of sometimes called the semi-classical Einstein equations. But this problem, I mean, it's simpler than the full solving for the full quantum theory of gravity for the black hole. Even if it's simpler, it's still complicated, because here you have a couple system. You have to solve for the metric, and then you also have to find the expectation values of the stress tensor in a dynamical metric. Okay, so you have to solve at the same time the quantum field theory in a dynamical background, and the geometry, the back reaction of the geometry, or the back reactive geometry of created by this stress tensor. So solving this complete system here simultaneously, that's something that's in general very difficult. Well, what one often does is to solve it perturbatively. You consider that, you first solve where the stress tensor is classical or zero. You find some geometry, then you compute what is the normalized stress tensor in that fixed geometry, then you back react, and then you go order by order, solving one side and the other perturbatively. And this is something that's, something is everything that you can do, but the insights that one gains from this procedure are in general fairly limited. We would like to be able to solve exactly for the problem of the back reaction. So I said this is difficult, but there are cases where one can do it, where one can account exactly for the back reaction by simplifying the system in different ways. One of the most popular ways of simplifying things is by going to low dimensions. Going to two-dimensional models, two-dimensional gravity is simpler. Two-dimensional quantum field theory, in particular, if you have a conformal field theory, it's also simpler. These are theories that we can make a lot of progress on. So a lot of effort on studying the exact back reaction of the quantum fields has taken place in this context, in the context of the CGH models, to the RST model, or more recently, a lot of attention has been paid to the case of where we have the theory of gravity is the two-dimensional Jakib-Teitel-Bohm gravity coupled to conformal field theories. And much of the progress that was made a few years ago in understanding the black hole information problem and the unitarity of the radiation was made in precisely this context. This is not what I'm going to talk about today. What I'm going to talk about is a different way of simplifying the problem and obtaining or accounting for back reaction in an exact way. And that's going to use holography in a crucial way. These other models, they can use sometimes holography or holographic language, but in principle, they are not fully holographic, or they are holographic in a different way than what I'm going to talk about here. So let me begin with something simple. Many of you are experts on holography and ADS-CFT, so this is also for people who are not so much experts on this. So, I assume that most of you have heard about holography one way or another. You know that this correspondence maps the quantum field dynamics of some quantum field theory, into classical gravitational bulk dynamics in one more dimension. The idea here is that you have some space, which is like ADS. This is the boundary of ADS. This is the bulk of ADS. It's a space that has some scaling property as you go towards the boundary. So the ADS boundary geometry, that's where the conformal field theory, we say that it lives. So dynamics of a conformal field theory in this geometry encodes all of the dynamics, the gravitational dynamics of the bulk, and vice versa. Okay? So the boundary here, the boundary of anti-density space is something that you can specify. You specify your boundary conditions. Boundary conditions for the field. And usually we choose boundary conditions so that this boundary is flat or spherical, formally flat, which is the same. Okay? So these are usually the boundary conditions that we take, where this is something that's conformally flat. But we can also consider other geometries. We just impose different boundary geometries, boundary conditions. So we could impose that our bulk geometry is going to be asymptotic to the geometry of some asymptotic flat space, possibly with a black hole. And then, when we do this, when we impose these boundary conditions to have a black hole at the boundary, then the holographic CFT lives in the presence of a black hole. And this is not a dynamical geometry. This is something that we impose as boundary conditions. So this is fixed background. So what we're saying here is that the state of the conformal field theory in the presence of this black hole, this is going to be dual to some classical bulk dynamics. So I impose this geometry at the boundary as boundary conditions for the Einstein equations in the bulk. And then when I solve the Einstein equations in the bulk with these boundary conditions, I have to solve them. That's in general not an easy problem. You know that solving the Einstein equations can be complicated. Then I'm going to find some bulk geometry. And the idea is that by solving the bulk geometry, I'm solving in a dual way for the CFT, this conformal field theory that lives at the boundary in the presence of this black hole. So this is kind of what I'm saying now. It's a summary. So as a conformal field theory in a black hole background, doing it holographically, solving for this bulk with this boundary condition amounts for solving the CFT, the conformal field theory, in the presence of the black hole. Now, when we have this conformal field theory, this is a quantum theory. It's a quantum field theory in the presence of a black hole. What do we expect to find when we have a quantum field theory in the presence of a black hole? Well, precisely what Hawking taught us 50 years ago. We would expect to find Hawking radiation. It's a quantum field theory in the presence of a black hole. It's a black hole that's surrounded by a radiation. So what this means is that this way of doing things, solving the gravitational equations with these black hole boundaries, black hole geometries at the boundary, that's something that can give us the quantum Hawking radiation. What I'm saying is that the quantum Hawking radiation of some conformal field theory in some fixed background, this is dual to some classical bulk dynamics. So we have to solve the Einstein equations to find it. And then that's going to give us the solution to this problem. Okay. So we're mapping a quantum problem, the problem of solving for the quantum radiation, to some classical bulk dynamics. This doesn't mean solving classical bulk dynamics. This is not easy. I mean, solving the Einstein equations is something that's, that it can be very complicated. But at least it's a reformulation that in some cases it may be easier. Okay? And that's this is an idea, the idea of using ADS-CFT to solve quantum field theory in the presence of curved spacetimes. That's something that's been studied over the years. But a little over 10 years ago, there was a review a good review written on the subject. And that's part nowadays of the lore of ADS-CFT. But the problem that we wanted to solve, so this is more like the problem that Hawking solved, the quantum field theory in a fixed background. We want not the fixed background, we want the dynamical background that's back-reacted, that's back-reacting to the radiation. Okay. Can we do this also with holography? Well, we want the geometry where the CFT lives, we want it to be dynamical. So we want the boundary of the boundary geometry of anti-de Sitter space to be also dynamical. How can we do this? Well, there's several ways of doing it, but the one that I'm going to be discussing today is what's called brain-wall holography, which is a fairly old idea, but it's been developed mostly in recent times. There's been quite a lot of progress. So the idea here is that, well, instead of considering that this boundary, the asymptotic boundary of anti-de Sitter space is at infinite distance, we bring it at a closer distance, and then it's something like a brain that can flap around. So the gravitating brain, so we put here some sort of brain, the tensional brain, is kind of a boundary, a wall boundary that can fluctuate. And it's known since work of around 25 years ago by Randall and Sondrom, that when you put these brains in anti-de Sitter space, near the boundary of anti-de Sitter space, then there's a mode of gravity that's localized on the brain. So you get a theory of gravity localized on this brain. And this means that this gravity, this geometry of this brain is dynamical. It's dynamics, and its dynamics is correctly described by a theory of gravity if this is anti-de Sitter space in d dimensions, then the theory of gravity on the brain is a gravitational theory in one less dimension. Okay? Because that's this geometry, as I say, it's fluctuating, it's flapping the brain in a way that its dynamics is described by the Einstein equations in one dimension less. So what we're saying is that holographically, so we had this theory, this theory that I had before, where we have the brain with gravity, but then we also have the bulk, and the bulk gravity, we have seen that solving for the gravity in the bulk, that's equivalent to solving for the CFT that lives at the boundary of spacetime. This was this mapping between the classical theory of the bulk and the quantum theory at the boundary. So what do we have here? So we have the brain, which is dynamical. It's a dynamical brain that's coupled in general to bulk gravity. This is a brain that's moving in anti-de Sitter space. Bulk gravity is the gravity in anti-de Sitter space. And we have a boundary, which is this dynamical brain. So we said that the dynamical brain that's equivalent to a dynamical boundary geometry whose dynamics is controlled by the Einstein equations. And we also said that bulk gravity is dual to some CFT. So what we have is that the dynamical brane coupled to the bulk gravity is a dynamical boundary geometry coupled to a CFT, and the boundary geometry that's governed by Einstein equations. So what we're doing, if we solve for this dynamical brane coupled to bulk gravity, we're equivalently solving for equations like this, equations that are Einstein's equations coupled to a quantum field theory. And in general, there are corrections because the theory of gravity that you require on the boundary is Einstein gravity in an expansion when this brane is not too far from the boundary, from the asymptotic boundary, not too deep into the bulk. So we get, at the end of the day, the idea here is that we're solving, we map the problem to precisely what we said before. Okay. So what we have is the Einstein equations that govern the dynamics of the brane coupled to the CFT that corresponds to the bulk dynamics projected on the brane. That's the quantum dynamics of the CFT. And this gives us the means to studying a conformal field theory in the presence of a dynamical black hole. Because if the geometry at the boundary is a geometry of a black hole, then, well, this CFT should somehow encode effects of Hawking radiation coming from the black hole. Okay. So a black hole on the brane, solving for the bulk theory of a black hole on the brane, that amounts to having the coupled system of the black hole and Hawking radiation. And the idea here then is that, well, if we have this, a black hole coupled to Hawking radiation, then this looks like it should give us the means of studying the dynamics of a black hole evaporation, this problem, mapping it to this other problem in the bulk. But the bulk dynamics is classical in the limit that we're considering. So the dynamics of black hole evaporation becomes the classical dynamics of a bulk spacetime with a black hole at the boundary. Okay, so this is a classicalization of the quantum problem of Hawking radiation. And this was the idea that was proposed in 2002 by Takahiro Tanaka and then by myself with Sandro and with Nemanja. Okay? And we wrote a few papers about this and made some conjectures that were studied over the years. So that's the idea then. So what we have to do in order to study a black hole coupled to a CFT in D dimensions, quantum field theories that you get in ADS in this holographic duality are typically conformal field theories. So the black hole coupled to the CFT is going to be equivalent to what we call a black droplet on a brane. Because the black hole, so we want to have a black hole geometry at the boundary, this black hole is going to stick out a little bit, or at least it's going to stick out to some extent into the bulk. There's going to be a black hole in the bulk that intersects the boundary, and the intersection of this bulk black hole with the boundary is going to give us a horizon also on the brane. So this is the picture that we want to, following the kind of pictures that I've been drawing before. This is kind of the idea that we want to keep in mind. I will often for simplicity, will represent it like this. I will just take a kind of the profile view. So this is the brane, this is this brane, this is the ADS bulk, and this is the black hole. As I say, when the black hole intersects the brane, then the intersection of the black hole with the brane is giving you a horizon on the brane, a horizon at the boundary, the black hole at the boundary. Okay. So this is the basic idea. Are there any questions? Does anyone want to ask any question?
Can I ask a stupid question?
Sure.
Could you just explain a bit more why putting the boundary brane makes the dynamics of the gravity on the boundary dynamical? Just a few more comments, please.
Yeah. So the brane can move. It's a dynamical
object. That's I understand. Right.
So then it can move, and then its dynamics, it's going to have some dynamics. And the dynamics is going to be induced by the dynamics of the bulk, of gravity in the bulk.
So this is a gravity on the brane. Am I understand correctly?
So gravity is, I mean, the entire system is gravitating.
Yes, yes.
Then, well, it's going to induce some dynamics on the brane.
Yes.
And then you can work out the equations that
Yes.
this dynamics on the brane this dynamics is induced by the bulk dynamics. And what Randall and Sondrum did is to show that the dynamics of the brain, that's control. I mean, that's essentially you take bulk gravity, you put some the Israel junction conditions on the brain, and then you see, well, you have a mode of bulk gravity that's localized on the brain. That's if you want, I mean, you're familiar with ADS-CFT, you know a lot about ADS-CFT, you know, but when you have a gravity in the bulk, you have a in gel, when you have a field in the bulk, it has a normalizable and a non-normalizable components. The non-normalizable is something that's fixed by boundary conditions at infinity. But if you, instead of having boundary conditions at infinity, you put them at finite distance, then this non-normalizable mode now becomes normalizable because it's not at infinite distance. It's normalizable, and then this means that it's dynamical.
I see. Okay.
This dynamical gravitational mode is the graviton that's localized on the brain.
I see.
Work out what equations does this graviton localize on the brain, what equations it satisfies. You find that it satisfies the Einstein equations plus possibly some corrections.
Okay. Thank you very much.
Thank you. Okay. Right. So this is the idea. As I say, this is flapping, and then as I say, the dynamics of this mode of gravity localized on this brain is Einstein gravity plus possibly corrections. So I'm going to, very often one discusses that this brain at in anticipated space is asymptotically flat, but I'm also going to consider here another setting, which is going to be useful for what we say, so this is anticipated space, you know that it's kind of a cylinder, and then I'm going to represent sections of the cylinder, spatial sections of the cylinder like this. And then, well, there are many ways. Anticipated space is maximally symmetric, so there's many convenient ways of slicing it. One way of slicing anticipated space is such a way is such that, well, you take slices like this. So this is anticipated space in d+1 dimensions. You can consider slices here, which are ADSD. This arrow should continue all the way to here. So this green surface over here that has also the geometry of anticipated space in one less dimension. This is nothing different than, well, if you take a sphere and then you slice it in such a way that the slices of it are circles. Well, here we're slicing ADS in such a way that the slices of it are ADS spacetimes in one less dimension. Now, when we do this slicing, then we can put a brain over here. So we take this anticipated space, we take this slice, and then what we do is here we place this brain, which is some surface with some tension, some object with a, I mean, it's a kind of a domain wall with some tension. And the way to construct this brain over here is that, well, we retain this part of the geometry, we throw away this, and then we glue this to another copy of itself. So we cut out this region, and then we paste it to another copy. So we take this space, we take another copy, we paste it to itself, and then this object is going to have some tension. It's the gluing is not completely smooth. The first derivative is continuous. So we paste it and copy, and then well, this is a kind of an orbifold construction if you want. And this is the construction of the brain wall that is a realization of what Randall and Sondrum did. It's a realization that was proposed and studied by Katz and Randall. And it gives theory of gravity that's slightly different. It's massive gravity, but I'm not going to go into these details. So the brain wall model that we want to study is something like this. Here we have the ADS bulk, and this is our brain. Okay, and then we said that we want to have some black hole localized on the brain, like this one. Okay. So we want to solve the Einstein equations, the Einstein anticipated equations with this brain and with a black hole localized here. So it's a problem of solving the Einstein equations. You may say, well, okay, that's something that I know how to do. How can we find solutions to this? Well, first, you may try to find exact solutions for the black hole on the brain, but that's very difficult. And we only have exact solutions in low dimensional settings. In particular, the highest that we can go for exact solutions for black holes on this brain, configurations like this, where we have an anticipated space with this black hole over here, they exist in ADS4. If you want to go to higher dimensions, then you have to do things numerically. And these are problems that are numerically, I mean, solving at least, well, I mean, when this was done a number of years ago, there was still kind of the kind of numerical problem that people regarded as difficult. Nowadays, people are much more numerically sophisticated, but it's you still have to solve some partial differential equations as an analytical problem. Something that well, you need some to do some coding. It's not something that you can do straight away with just some routine in Mathematica. And also, the problem with this is that, well, the kind of solutions that you study here, so far, these exact solutions or numerical solutions, they've only been studied in time-independent situations. And if you want to follow the evaporation of a black hole, then you would like to do something that's time-dependent. Now, that's a harder problem, but a few years ago, we realized that we could make progress here analytically or with much simpler numerics that you can do with ND-solve, by considering the large D limit. The large D limit where gravity in the bulk is a gravity theory in antithesis space with a large number of dimensions. And in this case, we could do time evolution as well. What I'm going to discuss today is not the numerical solutions. The talk is going to be mostly two parts. It's going to divide it in two parts. One of them is describing these exact solutions in antithesis space in 4 dimensions, and then also what we did in the large D limit with time evolution. Are there any questions? Any other questions?
I have a question. So in a large D limit, you also have a solution for the with time independent.
Yes.
Okay.
Yes. Actually, yes. I mean, I'm not going to talk about that. Well, that's part of a work that I did in collaboration with you and with Takahiro Tanaka and with Ryotaka Suzuki and Kentaro Tanabe. We did some of that. But what I'm going to talk about today is something that we did later, not just the static solutions. The static solutions are possible, and we made some progress. And what I'm going to discuss is a slightly different approach that we did so that we could also study time evolution.
Okay, thank you.
So, well, I'm going to first describe these low-dimensional models, ADS4. This means that the theory of the boundary is a 3-dimensional theory. This is going to give us exact holographic 3-dimensional quantum black holes. So how do we find, or what do we use for these bulk theories in antithesis space in 4 dimensions? Well, turns out that the solutions that we use are solutions that have been known in the literature since many years ago, since 1976. Many of you probably know that there's a general class of type D metrics that was found by Blavatsky and Demiansky, which are metrics that well, you can write them in this form. I'm not going to have to explain too much of these metrics. You may think that this is complicated or simple, depending on how familiar you are with them. They are metrics that can be written, as you say, in a simple form. They are not as simple as the Schwarzschild solution, but nevertheless, they are not terribly complicated. And they have here some functions, and the important function that's for us is going to be this function h of r that I will keep track of. These solutions, they were used for studying black holes on brains many years ago in papers that I wrote with Gary Gorovich and Rob Myers. You see the parameters that we have here. We have a parameter mu, a parameter L. This is a cosmological constant, and this is a sign parameter. So why do we use? I mean, these coordinates here, they may not be familiar with you. To you, and we have here a coordinate r, and we have a coordinate x. Their meaning is relatively simple. The metric is this one. This is because these coordinates are well adapted to describing a black hole in this brain. They will be. Okay, so these coordinates in the disk that represents antithesis 4, the coordinate constant r coordinates, r surfaces are like this, the circles, and constant x surfaces are like this. So you see here that x is kind of a polar angle, and r is a radial direction, but they are not centered at the center of the disk, they are off-center. So you have the center of the coordinates is some direction along this axis. And this is a way of foliating antithesis space in 4 dimensions, but you can also, the full solution with a mu parameter, non-zero, and so on, that actually describes a black hole because this function h of r has some zeros, and the zeros of this function correspond to horizons. And when you study geometry, then you find that what they describe is a black hole that's centered over here. Then we wanted to put this brain at some surface that satisfies these junction conditions. Turns out that this surface x equals 0 is a good place to put the brain. So you put the brain, you throw this away, you keep the rest, and you have this black hole localized on the brain. So this this solution, this anti-de Sitter 4, this solution to a gravity in anti-de Sitter 4 describes this black hole, a black hole localized on the brain. The black hole is a 4-dimensional in the bulk, but it's going to correspond to some, when we take the metric on the brain, it's going to be some 3-dimensional geometry for a black hole. And that geometry that we get at the boundary, at x equals 0, where we're putting the brain, well, we can read it, the geometry on the brain, by just putting here x equals 0, x equals constant equals 0, this goes away, g becomes, and then you find that the metric induced on the brain at x equals 0 takes this form. This is what we call the quantum BTC metric. And this is a metric that was studied early on by myself with Sandro and Nemanja, but a few years ago, 4 years ago, with Anthony and Benson, we studied it in more detail. And the geometry looks like this. So that's the previous geometry now projected on the brain at x equals 0. And let me tell you a little bit of what this metric looks like. This is some function of this parameter here. I'm not going to enter any details. It's something that can be fully obtained by analyzing the metric. So you see here that we have a parameter L. Okay. So when you set this parameter L to 0, well, in the geometry, what you do is that we had here the brain over here. When we send L to 0, we're moving this brain to the boundary. So L goes to 0, takes the brain to the boundary. When the brain goes all the way to the boundary, then it's harder to make this geometry fluctuate. It's being more rigid, and then what you have is that the geometry at the boundary doesn't fluctuate. What geometry do we have at the boundary here? Well, when we set L to 0, you see that this geometry becomes something that many of you may be familiar with. This is a 3-dimensional geometry of the BTC black hole. So when L goes to 0 and the back reaction goes to 0, what we get is the BTC black hole. And then what you're going to have also some stress tensor corresponding to the bulk here. That's a problem of quantum field theory in a fixed background, in the fixed background of the BTC black hole, when you get a stress tensor that corresponds to the quantum stress tensor in the fixed background of the BTC black hole. Okay. But we're interested in the case where we have non-zero back reaction, where this brain can fluctuate. So then we let L take a finite value. When L is positive, then what we get is a geometry that's different than the previous one, because it has this term over here with this function of the mass that, as I said, you can determine explicitly. This is what we call the quantum BTC or quantum corrected BTC black hole. Because you see here that now we have a BTC black hole plus some correction. This is the correction that's generated by the back reaction of the quantum fields in the presence of the black hole. Okay. So this is what comes from having this brain being dynamical in the presence of this gravity in the bulk. Gravity in the bulk is the CFT. So the CFT back reacts on the geometry at the boundary by generating these terms. So this is the metric of the quantum BTC black hole. And this is something that we could relate also to the metric of if you did the problem of the BTC black hole with perturbative back reaction, then you would get something that in many ways it resembles this. Not in the details of this, because this depends on having the CFT content that you have. But this structure, that these corrections go like 1 over R, that's general for a conformal field theory in the presence of the BTC black hole. So we get here a geometry, the quantum corrected, the quantum effects, the quantum back reacted BTC black hole. But we can also get other geometries. You know that in or in general, in 3 dimensions, besides black holes in ADS, the BTC black holes, you can also get conical defects. A conical defect in 2 + 1 dimension, that's a conical singularity. Can we get the effects of back reaction on a conical singularity? Well, yes, that's just another limit. You take these geometries, You consider other ranges of parameters. You can take the range of parameters where the mass is negative. You know that in anti-de Sitter space, in anti-de Sitter 3, for positive masses, you get black holes. For negative masses larger than a certain value, what you get is conical defects. So in general, yes, when you have the geometries without L, with L equals 0, with no back reaction, these geometries describe conical defects. So this is, with this negative mass, this would be a conical defect in anti-de Sitter 3. But when you consider, you take these geometries with L positive, then these geometries, they develop a horizon. So instead of getting a conical defect on your brain, your conical defect is now surrounded, is now dressed by a horizon. So you get a small black hole in anti-de Sitter 3, a black hole in this range, where normally you don't have black holes, you only have conical deficits. Here, what you're getting is that this conical deficit is now dressed by a horizon. Where does this dressing of the cone come from, this small black hole? Well, a quantum field theory in the presence of a conical defect has some Casimir energy. What we say is that this Casimir energy, the stress tensor of this Casimir energy, it can back react on the geometry of the cone, and the back reaction creates a horizon around the cone. So the Casimir energy, the back reaction of the Casimir energy on the cone, is hiding now a conical singularity inside a horizon. So this is kind of a quantum cosmic censorship. Quantum effects are dressing a singularity. Okay. And this is a phenomenon that we discovered with Nemanja and Sandro over 20 years ago.
Roberto, sorry, I
Yes.
have a maybe stupid question, but why L is positive?
You can L is positive because otherwise you get pathological metrics if you want.
Oh, I see.
I mean, it's the range of L here has to be positive if it's a question of regularity.
Oh, I see.
It's just regularity. Okay. Yeah, you would get this. It's because otherwise you would get a brain with L is proportional to the tension of the brain. You want the tension of the brain to be positive. If you take L negative, you get a negative tension brain. You can also study those solutions, but they are not. They don't localize gravity on them. So I mean, it's possible to construct the solutions, and they would be. You wouldn't have a gravity localized in the brain because, as I say, the tension of the is well. You know, brain works. I do. So you know that a negative tension brain is not good for Randall syndrome or brain wall. It's negative tension.
Okay. I see. Thank you.
Yeah.
So, sorry, Roberto.
Yes.
Yes. May I ask what do you mean by Casimir energy on a cone? I don't fully understand what this means.
So, well, I mean, you put a quantum field theory. You know, quantum field theory. I mean, Casimir energy. What I mean is that you're changing boundary conditions for your field, or you're changing the conditions. You're changing the periodicity conditions. It's a topological effect. So, because going from flat space to a conical deficit, that's changing identifications.
I see. So it came from the CFT contribution. Am I correct?
Yes, exactly.
Okay.
Yes.
Thank
But
you.
CFT on a cone, you can solve it by the method of images. If it's a discrete cone, like an orthopole.
So it's a back reaction by the CFT contribution.
Exactly.
Okay, thank you.
Can I ask?
Yes.
So in this case, your horizon is localized on the brain.
Yes.
But can you also construct a configuration that the horizon actually extend towards the bulk region so that like a black string?
Yes. Yeah, so it's possible to consider those geometries where you have the BTC black hole, for instance, you can also have a black hole or a black string in ADS. And those are interesting and mysterious, a little mysterious. I will mention a little more about them later when we discuss the ADS. But for the BTC black string, you know that this can be studied. It's mysterious in the sense that, well, the geometry in the brain is exactly BTC. The stress tensor is exactly 0. Why a CFT in the presence of a black hole can have a completely 0 stress tensor, but the state of the CFT is still non-trivial. These configurations, I think that they are still not very well understood, the black strings, the brain, because it's a non-trivial state of the CFT in the sense that there's a non-trivial entanglement structure. You can compute quantities which are non-trivial, but the stress tensor of the CFT is 0 up to anomaly.
Okay.
And that's something that I think it's not very well understood. It's a property of holographic CFTs. Free
Thank you.
CFTs wouldn't have this property, as far as I know.
Roberto, can I ask a question? So,
Sure.
so this L is an orbital parameter or Einstein gravity? I mean,
Yes.
L needs to solve the Einstein equation or
Yes.
4-dimension.
Yes.
But
Yes.
you said that this L is related to tension. So do you impose some boundary condition at the X equals
Here,
0?
what we're imposing is the Israel junction condition.
I said, and that tension parameter is related to L.
Yes. Yes.
I see. Thank you very much.
Yes. So the parameters in the solutions are essentially two. Well, I mean, there's the bulk cosmological constant, which you can trade for this L3, the 3D and the 4D are related. So there's the bulk, so there's three parameters: cosmological constant, the bulk, mass parameter, and back radiation parameter. This is related to the brain tension. This is related with the brain tension to the bulk cosmological constant, and this is a parameter that tells you how big or small the black hole is. These are geometries with these three parameters. And then, well, one of them you can choose to set the scale, say you take this to be 1, or you take the bulk cosmological constant to be 1. And the other parameters tell you how close or how far to the boundary the brain is and how large the black hole is. So these are these small ADS black holes. They also exist with asymptotic flat brains. We studied them with Sandra and Nemanja. But more recently, we also realized that, well, we could use these geometries also to study black holes in de Sitter 3. De Sitter is a geometry that, you know, in general, you don't have black holes in de Sitter 3. You can have cosmological horizons. But now you can also consider, well, a conical defect in de Sitter 3, and then the quantum back reaction is going to dress this conical defect with a horizon. So you can get a black hole in de Sitter 3, and it's going to be a quantum black hole. The way to do it is by considering the same class of geometries that we discussed before, the Plebanski-Demiansky geometries. Now what you get is, well, something that looks like de Sitter, but with a quantum correction. And the foliation is something like this. Instead of having the brain extending to the boundary, these are compact brains, like the compact sections of de Sitter, and you get black holes on the brain with are at the two antipodal sides of de Sitter. So that's something that we did a couple of years ago, and we studied in some detail. Now, with this, I could give you more details, but with this, I finished the discussion of this first part, how well, we can use these exact solutions that allow us to have a quantum back-reacted black hole and the CFT stress tensor, and we can describe it in these cases, at least the three-dimensional cases, exactly and in detail. I think that this is a very good example of how you can use holography very efficiently to solve a problem that in general, it's a very hard problem. With this, I'm now going to go to the second part. I still have some minutes to do it. It's to describe the holographic duals of evaporating black holes. And that's more recent work. As you see in many of these papers, there are people from Japan involved, some of my Japanese friends and collaborators. So in this case, what we want to study is well, more details of radiation, in particular to see whether we can do dynamics. As we've been saying, well, the black hole is black hole coupled to a CFT radiation. For the black hole, what you take is a bulk horizon that intersects the brain, the picture that we had before, and the thermal CFT radiation corresponds to a horizon in the bulk. You know that in general, in ADS CFT, when you have a horizon in the bulk, your CFT, the dual CFT, is going to be in a thermal state. So the picture that we had before, these droplets, they correspond to some black hole surrounded by some halo of CFT. You can also have configurations, or you can imagine having configurations where the black hole sticks more into the bulk. So this is going to be more a bigger halo of radiation around the black hole. The black hole here is small, but there's a large halo of radiation around it. And then you can also consider situations where the black hole is not intersecting the bulk, and then this black hole is going to correspond to just thermal radiation on the brain. Now, one configuration that I'm going to discuss before, but I haven't discussed so far, well, it came up in the Akihiro's question, is the black string anticity space. This is a black string which extends all the way from one boundary to the other. It's an exact solution that is very easy to find. It's like other black strings. You take them by taking a black hole in one less dimension and then extending it in a uniform way along the z direction. Now here, this black string intersects the boundary geometry at 2 points. So you have one black hole here, another black hole here. Black holes are the antipodes of the boundary of a digital space, which in general is a sphere. So this is a black string in ADS, but we can, that was without a brane. We want to introduce a brane. The brane, we introduce it in the way that I discussed before. We can introduce a brane like here by cutting out this region and then gluing it. And then this is going to give us a black hole on the brane, and then also extending to the other boundary. Sometimes I will want to consider that I have not just one brane, but I have two branes. I think that Tadashi calls this wedge holography. And then what you can consider, you can very easily construct a solution that describes what's sometimes called the black string or uniform funnel. But you can also have droplet configurations, like a double droplet. And then if you have one brane, you can consider a single droplet. And there are other configurations. I'm giving you here pictures that will appear later. This is a bulk black hole. So here you don't have a black hole on the brane. What you have is radiation on the brane. Now we want to study this system to solve this for all of these configurations and possibly their dynamics using some method. And the method that we're going to use is the large D approximation that we developed. We began developing a number of years ago with Ryotaka Suzuki and Kentaro Tanabe. We began this program in 2013. The version that we're going to use later, we developed in 2015, but there had been previous work, as mentioned, with Tetsuya and with Takahiro, where we were doing the static case. But the version of the system that I'm going to describe is the one that we did with Ryotaka and Kentaro 2015. The way that large D helps, I'm not going to talk too much about large D. Large D, one of the things that it does is that it simplifies the dynamics of black holes by decoupling gravity and localizing the dynamics near the horizon. So there's these two things. All of the dynamics gets very localized close to the horizon because of the steep gravitational potential, and also emission of radiation is suppressed. So you can have dynamical horizons that are non-linearly evolving, but without emitting radiation, and this simplifies things a lot. As I said, I'm not going to go into details, just to give you an example, the way that we develop effective theories where all of the Einstein dynamics, for instance, for a black string, they are reduced. All of the Einstein equations reduced to some simple equations that describe how the profile of the horizon changes along some direction. So if we had things like the black string that I showed you before, the fluctuations of that horizon, they're going to be described by a simple set of equations. And these equations are simple enough that you can very easily, even if you don't know how to solve them numerically or analytically, you can solve them numerically with ND-solve. So we obtained in our papers, the papers that I mentioned before, the dynamics of a black string and objects in antithesis space, and then it's easy to find solutions. This is, the boundary of antithesis space would be here. This is a black string. I'm going to draw different pictures. So this is the kind of idea, the cartoon picture. This is this cartoon, this is the horizon, so it's uniformly extending here. I put it correct here, but this is corrected here. So this is straight, and this is the picture in the bulk. Okay. So this is a funnel, these are the boundaries, this is the funnel. This is the simplest configuration, this is exact, but you can easily find it. But there are other configurations that you have to find by solving the equations. So as I said, solving them numerically is easy. So that droplet looks like this. Something like this. What you have to bear in mind is that black holes in the large D limit look not so spherical, but they look like Gaussians. That's something I could explain. But essentially, whenever you see in my pictures some Gaussian, this corresponds to this kind of horizon. And then this is this picture. So this is this Gaussian rotated along the axis. It looks like this. Okay, so this is a double droplet. But we can also have a bulk black hole. It's going to be this Gaussian at the center. It's not intersecting the brane, and like this. Okay. So these are static solutions that are easy to find. Now, can we do dynamics? Can we let them evolve? And this is something that we can, and I'm going to show you how. So say that we have here, we begin with a black hole in the bulk. And then I'm now going to kick it so that it goes to the boundary. I'm now throwing it to the boundary. So a black hole in the bulk is some radiation. Throwing it to the boundary is, well, collapsing this radiation. So what do we get? Well, this is the result of a simple numerical simulation. You see what it's done. Let me do it again. So we throw it, it goes, and then it sticks to the brain. It remains there. So what we have done is this radiation on the brain, it's collapsed and formed a black hole. So this is the process of collapse on the brain. You have this thermal blob. This black hole corresponds to a thermal blob of radiation. We throw it to the brain, and then it sticks there. So this is collapse. Can we do evaporation? So let's begin with this uniform string, this uniform funnel here. And then I'm going to perturb it in a particular way. So what do we get? I perturb it. And then now I don't have a black hole on the brain anymore. I don't have a Gaussian on the brain. So this black hole has evaporated into the bulk. I can also perturb it in a different way. That does this. I will explain you later how to understand this, but what I've done here is that this black hole here has evaporated into the other brain. And then I can consider another situation where I have a black hole in the bulk connected to a black hole in the brain, a smaller black hole in the brain here. This is the black hole in the bulk. I set this up as initial conditions. I let them go. And this is what the simulation does. So what has happened here? The black hole at the boundary has disappeared and has gone completely into the black hole in the bulk, which has grown because it has absorbed all of the horizon that we had here. So this is what we had. This has disappeared, and now what we find is that this black hole in the bulk. I'm going to explain to you now in a few minutes, in a few minutes left, how can we understand this as a holographic black hole evaporation. So what is the reason that we can have this holographic dual evaporation? So we have that the black hole on the brain evaporates by funneling radiation into some horizon in the bulk. So in the simulations that I showed you, we had some black hole initially on the brain, and then it's flowing into into the bulk. The horizon in the bulk, something that it happens in the configuration that we had, the horizon in the bulk is colder. So you can have a measure of the temperature of the black hole horizon in the bulk, and that's colder than the black hole on the brain. So what we have is that the colder black hole is absorbing energy, radiation from the hotter one, which is the way it should be. Heat flows from the hotter system to the colder one. This, in our case, it requires to have that the black holes are connected. We have all of the black holes connected. The black hole on the brain was connected to some black hole in the bulk or at the other brain, and they are connected through some horizon. This is what allows heat to flow from one system to the other. Having this horizon extended in the bulk, this means that you must have some entanglement channel in the bulk. This is the black funnel. So let me now go to the previous simulations and show you what happened. So we had this uniform funnel, which corresponds to a black hole here, another black hole here, connected through the bulk. And these are hot black holes. The way that I perturb this initially, this configuration is that I decrease this a little bit, I increase it here. This is becoming smaller and hotter. This is becoming bigger and colder. And then what is going to happen? That the hotter black hole is going to emit radiation into the colder bulk. And this is what it did. So the dual picture is that I have these black holes, which are hot, and then they are radiating, both of them, into the bulk. Another simulation that I showed you was I started with a different perturbation. These two black holes were initially the same temperature, but now I'm making this slightly hotter and this one slightly colder. So what we're going to see is that radiation is going to flow from the hotter to the colder. So we have a hot black hole radiating into a colder one. And what it does, the radiation that this black hole is emitting is accreted by this other black hole, which then has grown. And this is the final simulation that I showed you. We have many of them. By the way, these simulations, they are very easy to run. In a few seconds, you get them. There are days when I said one afternoon I had evaporated 100 black holes or something to see different effects. So here we have this black hole here, which is hot, connected to a colder black hole in the bulk. And then this is going to radiate into this one, because this is hotter and this is colder. And then what we have is that this is emitting radiation in this way. And then it completely evaporates into the black hole in the bulk. So the hot black hole evaporates into the colder path. So what I've shown you is that, well, the takeaway from these simulations is that we have been able to fully classicalize Hawking evaporation. The dynamical evaporation of a black hole, described through holography, describes in a classical bulk evolution. The classical bulk evolution of these bulks is the dual of dynamical evaporation. And what we have is all of these classical black hole horizons. What they are unstable black hole horizons. This is the same phenomenon that drives things like the Grover-Laflamme instability. So the dynamical evaporation of a black hole describing holography is dual to some horizon instabilities. And what I've argued is that, well, we can very easily understand this. You see, well, which part of the black holes that I have is hotter and which part is colder. Then the evolution is going to go from hot to cold through some funnel that occurs in the bulk. So you have hot black hole evaporating into colder degrees of freedom. Now I'm coming now to the end of my talk, to my conclusions. I hope that I've been able to convey the idea that describing quantum black holes as holograms in a brane world, that's something that provides an efficient solution of the quantum back reaction problem, because we've mapped it to a classical bulk problem in one more dimension. It's still non-trivial, it's not easy, but in many cases it's doable with exact solutions, numerical solutions, or with approximations like the large D approximation. And what this has given us is, well, new quantum black hole solutions in 3 dimensions from a 4D bulk. And then using these large D methods, we've been able to see how Hawking evaporation can be classicalized. Of course, this doesn't mean that this is just the panacea, the way to solve all problems. It has also limitations. For instance, one of the big limitations that we're always limited since we're doing classical dynamics in the bulk. This means that we're always in a regime where the CFT is a conformal field theory, the limit of infinite coupling, and infinite N. And this introduces a number of peculiarities that we're puzzling over for a number of years, which I haven't discussed. But this is one of the limitations. You have to learn how to think about it, because these quantum field theories in the presence of these black holes, the infinite coupling limit and infinite N, sometimes they have properties that are different from the ones of free field theories. And then another limitation is that in everything that I've been doing, this has been bottom-up holography. It's not something that I've derived from a string theory embedding. There are in some cases, one can construct string theory embeddings of this. I've done it in a more effective field theory way. I've introduced a brane in the bulk. And then, well, what this means is that there are limitations because the theory that I have is not fully UV complete. I haven't told you how to derive this brane from string theory or how to embed it. But nevertheless, as an effective tool, this is still very efficient, and well, one can try to improve it in different ways. And there's people who have been working on this. Some of you have been also work along similar ideas. But with this, I'll stop and thank you for your attention. Thank you.
Very much. Thank you. Thank you very much. So if you have any question, please unmute your mic and ask questions.
May I ask a quick live question?
Yes, of course.
I am Takahiro Azuma, and thank you for your talk. And I wonder whether this black hole transition is related to the Gregory-Laflamme transitions of black hole.
Yes, yes. This is one of the things that I kind of I didn't say too much, but they are related. So the things like it's probably this one, for instance. Let me
Yes.
see. This is a Gregor-Laflamme instability.
The black holes
Yes.
is merged.
Yes. So
Two black
yeah.
holes
So
become one.
this. Yeah. So this is going to keep pinching. At the large limit they don't pinch, but this is essentially a Gregor-Laflamme instability. Yes.
Yes.
So
Thank you.
I think it's something that's maybe a little surprising that Hawking radiation, in this case, is mapped into a Gregor-Laflamme type of instability. But the Gregor-Laflamme instabilities are very general properties of extended horizons, long horizons. Yes. This also, I mean, this is a bit more complicated, but it's also on the. Yes.
Can I ask a question?
Sure.
So, yeah, in one of your example, you start with some bulk black hole, but in the end end up with boundary black hole. Some have solved.
Yes.
So that's case, but final setup is that a static configuration? So localized.
Yes.
Plane. Do you
Yes.
have some physical understanding of this? How, I mean, if we have some black holes, then we have a Hawking radiation,
Yes.
but it looks like really static. So
Yes. They are static and stable. So this was something that puzzled us for many years. Actually, initially, Takahiro and also Nemanja, Sandro, and I, we conjectured that static black holes on the brain shouldn't exist because they should have Hawking radiation, and Hawking radiation should be emitted. Well, and this was a conjecture that was open for a number of years, and people here, like Yoshino and others, contributed to this. People in Japan contributed to this problem. Why? I mean, is it possible to find a static, stable black hole on the brain? For a number of years, we thought that it wouldn't be possible, but then, well, numerical work, I think it was concluded. The most conclusive work was this work by Figueras, Luccietti, and Weisman. Why does a black hole, which is a hot object, not radiate when it's coupled to a quantum field theory, not radiate to a cold infinity? I think that the problem here is that you need to have some connection between the black hole. Let me see how I'm going to try to find a picture where you can describe this like this one. Okay. So here you have this black hole. If it's going to radiate into the bulk, then this black hole should slide off the brain. And that's something that the black hole doesn't do. And that's one of the things when we got the simulations running, we wanted to see, is this stable? And then we tried. I mean, they are not numerical solutions, but we could study them numerically very well and perturb them. What we found is that this is it's stable. So in order to evaporate, what we need to have is some connection between this horizon here to some other colder system. You need to have some funnel, some entangle your degrees of freedom here. So you want to, here you have some UV degrees of freedom, and then you want to connect them to some IR degrees of freedom. For this to happen at the classical level, you need to have a bulk horizon that connects them so that you can have bulk generators flowing to the bulk. This is the bulk point of view, that you need to have this connection. It's something that I think is a property of the infinite N and infinite coupling limit. That in the infinite N and the infinite coupling limit, then there's a disconnection between this black hole is perfectly insulated from the infrared degrees of freedom. If you have, say that you put now here some colder black hole here, but they are not connected in any way. If they are not connected, there's no way that this black hole is going to classically evolve into the other one. Okay. So we could put, and that's something that we tried, to put some black hole here. I could even run some simulations, but I don't have. You put some black hole here, you put a black hole here, and if they are not connected, if there's no connection, they are insulated. They are separate degrees of freedom in the CFT. You have some UV degrees of freedom around the black hole. You have some IR degrees of freedom, which are also thermalized, but in the infinite N limit, they are completely disconnected. I don't think that we have a very good understanding of this from the quantum field theory point of view, and I think it would be interesting to understand it better, but I'm pretty sure that it's an infinite N, I mean, strictly infinite N, strictly infinite coupling.
I see. So that limit, large N limit, so we don't have
Yes.
any Hawking radiation for this static configuration.
Yeah, for the static configuration, well, you have this halo of radiation,
Yeah.
but this is stable halo.
Also,
Which
do you
is
think
something that can happen at finite coupling.
I see.
Yes,
Do you think also strong coupling is also important?
I think so. I think it's infinite coupling. Yeah.
I see. The specialty.
If we include the finite coupling corrections, say string theory corrections, I think then this would it will become unstable. It would be interesting to study this. Nobody has done this as far as I know. I mean, to include corrections to this and show that quantum bulk corrections, that's going to be finite n corrections, 1 over n corrections. They are also going to, because in that case, if you have a quantum bulk corrections, then this black hole is going to emit radiation into the bulk, and then it's going to have radiation. Finite coupling, finite string theory effects, I don't think that they have been studied, but I would also expect that they change the picture. It's complicated to solve, I think, but I think I haven't thought too much about how to do it, but it would be interesting if something could be done.
Yeah, that's very interesting. I mean, unusual, but it's very interesting behavior. Yeah, I have no. Yeah, that's also a big problem for I mean, initial stage. But I see. But your calculation really, I mean, very beautifully solved. Anyway.
Yeah.
That's good.
Yeah. Largely, so for us, it was for many years. I mean, doing dynamics in these cases, we didn't know because doing it in full numerical relativity.
Yeah.
Dynamical evolution. But then it's complicated. That's very difficult. But with large D, we could do a lot. Of course, it has limitations, but we could do these things, and that was very efficient. Very nice that we could do it.
I see. Yeah, that was very nice. Yeah, thank you very much.
Thank you.
Any other questions? So I have some naive questions. So this is actually a brain world black hole, and
yes.
So, but basically we can think that they satisfy the semi-classical Einstein equations. Yeah, yes. And in the three-dimensional case, it's special, but in a more than three-dimensional case, maybe you have a higher curvature corrections, and
yes.
In that, then such a higher curvature correction might modify the entire behavior. Is there such possibility?
Yeah.
Do you think corrections are more?
Well, the corrections, we know how to derive the effective theory on the brain.
Yeah.
That's using essentially holographic normalization, but keeping a cutoff fixed.
Yeah.
So we know how to do that. They are going to have some effect. Of course, so the there's a parameter controlling the strength of the higher curvature corrections, which is essentially the L parameter. So when L is very small, you're close to the boundary, and then higher curvature effects is going to be small. If you move it farther into the bulk, then they are going to become large. And at some point, they may have an important effect. But then when they become very large, you should change you don't have, so if you're in a 5D bulk, then you have 4D gravity. When these higher curvature corrections, they become very large, then instead of 4D gravity, you're recovering 5D gravity dynamics. So you're losing the effective theory, the effective four-dimensional theory on the brain. You're going away from the regime of validity. But in principle, they can change the behavior. But this hasn't been studied too much, as far as I know. The solutions in ADS5, they are known numerically, and they are only known for very small back reaction effects, because they are very close. The solutions by Pau, James Lucchetti, and Toby. They were, and then there was later work also by George Santos and his student Biggs, where they also studied the rotating black holes. But numerically, that's complicated. And doing dynamics, which is what would be most interesting, that's a very difficult problem. And you have to convince numerical experts to do these time evolutions.
Uh-huh.
Yeah.
Okay, thank you. Any other questions, comments? If not, then maybe it's time to stop. And thank you very much for very wonderful talk. And let's thank Roberto again.
Thank you.